you can, so, and 1 point here, and 1 point here, something like this. And so what's going to happen is I'm going to have two centers, say here and here, associated. And so I'm going to get, I'm not sure, well, let's say here's maybe how I can do it. I have 2 points directly on top of each other. So this is times 2. And now I have 2 centers here and here. And then the Voronoi edge goes right through this point. Okay? And so there are 2 points here. One of them I'm going to assign this way, and one I'm going to assign this way. And then I recalculate the centers and I switch the assignment. So the cost has not changed, it's the same distance. So maybe something weird like this could happen. And you could actually have the same set multiple times. In this case, the centers aren't changing. But maybe you could come up with an example where the centers do change and they do 2 things and the cost is the same because there was some tie. It was the same distance. So if you're doing this and something weird happens, you need to worry about whether you need to break ties in some way which is consistent. So if the distance is the same, always assign them to the one with the smallest index, the center with the smallest index. So that would be one way. If you did that, then you can't. Then there's a total ordering on all of the possible constraints. That's a good one. A more serious problem is actually in the numerical error. You may actually calculate centers of 2 sets, and because of where you place the centers, when you calculate the sum of the distances, it actually increases because of the numerical error. And that could happen probably, so this algorithm is pretty stable. You're not actually changing the data at all. You're just changing the center and just getting averages, and this is not going to cause too much numerical error. There's another very similar algorithm that converges in a similar way for kind of matching point sets, and I've worked with this, and this does some weird rotations, and that one has the same kind of convergence properties and the same kind of proof that it should never get stuck in something like that, but because of numerical errors, I've had that one get stuck. So that definitely can happen. So that is a good point. If you can say that it will always converge, but you need to watch out for numerical issues sometimes. But in k-means, I've never heard of a case where that actually happens.
I'm thinking even if you don't break the tie, it's eventually going to converge because of the pigeonhole principle, right?
Well, you could have 2 similar states that go in between them. You could have, clustering number 1. You could have clustering 2 and clustering 3. And this one always assigns centers which lead to this clustering. This one assigns centers which lead to this clustering. This one assigns centers which lead here. And they all have the same cost. In theory, it could happen. That's enough of this conversation. These are issues that won't really happen. So we still haven't totally answered this. So in practice, it will converge when things don't change. But this could be a really large number. In fact, people have there are these examples where it takes this long. And this is not typically how it's implemented. When I was a grad student, I implemented versions of k-means. I implemented it this way. I waited till things were actually stable. But in practice, this is not what people use. They will still call it when it converges, but it usually means something else. They'll actually look at the cost function, and they'll say something when, so a cost at the end of iteration I, and they'll divide it by the cost at the end of iteration I minus 1. If this is less than, say, 0.001, then they stop. Or this is this one's always larger than this, so this should be less than 1 point, something like this. They'll set some threshold. Or they'll say when say, the cost to buy, or maybe they'll look at the difference between these, the subtraction instead. Or when they just say when the cost is less than, you know, some threshold. Or even in practice, often what people do is they'll say that R is equal to 10. We're going to run this 10 times and we'll stop. And that usually works pretty well. You can run it 10 times. It's going to keep getting better. And usually what happens is the first 2 or 3 rounds are going to do almost all the work. After that, it's very minor tweaks. It's things on the boundary. And usually, you know, 10 is probably maybe even an overestimate. That's being conservative. If you ran it for 5 rounds, you're probably fine. So in most cases, people will look at some threshold like this, or they'll just run it for 10 steps. So, okay, so what else? So I'll mention there's a couple of other, relating to this thing, there's been a couple of other theoretical papers that say these cases where it actually runs exponential these are kind of contrived cases. If you jitter all the points, perturb them a little bit, then they can show that it's some hideous polynomial like n to the 34. You also don't care about, right? Or if the points are on the grid, then it's known to run in like, I think it's close to linear number of steps. But still, you can use 10. Okay, so the other point that we haven't talked about, so we've talked about how to kind of do these number of rounds, this convergence, y converges. We haven't talked about this part yet, so we need to choose some sets. So in the Gonzalez algorithm, it really didn't matter so much what point I picked. Here I'm picking actually a set of C points, a set of these K points. And this can sometimes make a difference, right? So when I say you can run it for 10 rounds and you should be done, that's generally true, but unless you pick the centers really poorly. If you do something kind of stupid here, you may get into trouble. So let me try and draw an example here. So let's say I have data here. Data here and the data like this, right? So you would say there are probably 3 clusters, right? It should be 1, 2, 3. But if you start by choosing a center here, and a center here, what's going to happen? Okay, this is my initial set. I'm going to get some way of dividing the points like this. Okay, so well, I'll run one round of this. Let me just choose a new color. So this center is going to move to be right here, and maybe this one to here and this one to here, but really this is not changing really this red line. Maybe this red line changed a little bit, but this one is basically the same. Okay, so maybe I move some points back and forth here, and this may take a few rounds to resolve. But really, I have not clustered the points in the right way. These should be 2 clusters, this should be 1 cluster. So it does not always give you the best answer. Probably actually, yeah, so choosing the centers poorly can lead to some bad results. Okay, so what are some ways of choosing centers? So what would be better than arbitrary? What if you were to, now I can't, if I knew the clusters, yes, then I just pick the centers of the clusters, right? But I don't know anything about the points. I don't want to spend too long. This is basically, you know, this I can basically, if k is going to be small, this is If k is a constant, this is basically linear time if the number of rounds is 10, right? So I don't want to spend too long on this. I don't want to spend more than linear time on the solver. So how would I choose the cluster centers?
If in case you are aware of the distribution, then probably the peaks of the distribution.
Yeah, but okay, so
yeah, you
how
might
would
not be aware of.
Yeah, how would I pick the peak of the distribution? So there you can kind of pick peaks of the distribution of points. So this requires defining what you mean by distribution and stuff. And there probably is actually a way to do this in near linear time based on various techniques. There may be a paper written based on trying to do this. So it's not a wrong answer. So, but what? There are various ways to define it. This is, I'm looking for other solutions. So don't. This is not what I would recommend. But
I think you could go for a pretty naive one. Just say like, no two centers can be this close to each other. Like have a minimum distance between each.
yeah, so that's good. That's good. But how would I do that?
So yes, you can do it. Yes, every time you consider a point as a center, you just look to see if it's check its distance against every other center, and if it's false.
Keep looking that way. So let me keep walking over here.
So
yeah, so one way you can do is you can run this Gonzalez algorithm. Right? If you run this guarantees that no two centers are too close to each other. Right? If no point is too close to the closest center, that includes the points which are the centers, right? So this is forcing the centers to be far apart. Right? So this is actually a great answer. So so the first thing you can do is you can run this Gonzalez algorithm, and this will actually give you good seeding, right? You said the Gonzalez algorithm ran really fast. It was very general. The problem was that it kind of picked points towards the outside of the centers, the outside of the data set. And that may not be representative. I mean, one, you want the kind of the assignment of the points to the centers, but the other thing is you want representative points for each of the centers. And these points are not very good representatives. So one heuristic you could do is you run this and then you have these points be the average of all the points they represent. If you're doing that, well, you've already run the first two steps of this iteration, and then you can repeat this for 10 more or 5 more steps. Yeah, so that's a great answer, right? So one way is to run Gonzalez.
We can put a threshold on the radius of the cluster.
Put a threshold on the radius of the cluster. So what does that mean? Is that a way of seeding it? How do I get the centers out of it?
I mean, the radius of the cluster will be fixed. So I mean, it should be approximately like equidistant from the boundary points in the center.
Yeah. So one thing you could think of instead is instead of picking once you have the set of points, you could try and put a minimum enclosing ball and take the center of that minimum enclosing ball, right? So I could take these points and I could pick the point which minimizes the distance. It's the smallest ball that contains the points. You can actually calculate that in linear time. Yeah. But that's not telling me how to get the centers. I can get one point that way from the minimum enclosing ball of all the points, but I want a set of k of these points, right? Or C of equals k. So this is kind of close to another approach, which is not necessarily a bad idea, but so one way is to, let's say, start with step 2 right? And do a random assignment, right? So I can sort by randomly come up with this function phi c. So I haven't defined where the centers are, but I've assigned all the points to classes. So I run to the points and I randomly assign them a number 1 through k. And then I start with step 2 and I take the average. Right? So this turns out not to be a good thing. So what would happen here that may not be great? So if I picked, so let's say I picked a subset of these points on random, right? I picked n over k of these points. Where is the center probably going to be? It's probably going to be in the average. And if I picked a different subset of points, the other center is going to be right here. You're going to get all of your initial centers somewhere in the middle. And that's, really not helping you very much. But if instead, so what makes more sense than this is just pick k points at random, okay? And set these to be the centers. So actually this is going to have an advantage over this Gonzalez algorithm. One of the issues with the Gonzalez algorithm, which I forgot to mention, so good thing I remember now, is that it's really susceptible to outlier points. Right? So let's say I had say 100 points here. So 100 points here, 100 points here, and then I have 3 points like this. Or maybe I have 2 points here, right? So what's going to happen, I'm going to pick some point arbitrary as the first one, the second one will be out here, and the third one will be here. I'm not really capturing, even if this number was 1,000,000, I'm still picking these far away points. I'm picking these outlier points. Gonzalez is going to tend to pick outliers. Now if I pick points at randomly, I'm very rarely going to pick these points, unless if there are a lot of them, okay, then I might pick them. But if there are very few of them, I'm going to tend to pick points in the middle here. I'm much more likely to pick points. I may end up getting 2 points in the same cluster. So one thing that you do is instead you pick something like k log k points. Okay, so I'm going to get an extra log k factor points. I'll run k-means with these points, and then, so I'll run with these points with an extra, so if k is 10, then this is like maybe I do 20 points. 20 or 25 points, something like that. And then at the end, I'm going to, so I just run, and then on these points, I do something like Lloyd's algorithm on this, so I'll call this set C prime, on C prime, and I'm going to pick out a set C. Okay, so what I'm going to do, I'm going to oversample. I wanted 3, I'm actually going to pick 5 points. And then on these 5 points, I'm going to kind of pick, I'll do something where I kind of combine together points which are close. So I'm going to say, well, these points are pretty close, so I'm going to get rid of this one. And this one is close, get rid of this. Now I only have k left. Because I picked them at random, I tend not to get the outlier points. There's some ways to assess there are no points around this point. We'll talk about outliers later on. There are ways you can kind of say, if I happen to pick one of these outlier points, I can not use that one. But if I pick this extra log k, there's a good reason why that should work.
Never mind.
Okay, so why does this extra log k factor help? Okay, remember the first lecture, what we talked about. We talked about we talked about the birthday paradox.
The heap data structure.
The heap,
Heap gives maximum.
yeah, well, so we're not saying how we're going to do this. You could, so this, you often see this as a runtime for data structures, maybe like a heap. But why does the extra log k factor points at random? Am I probably going to get one in each of the, kind of, if there are k clusters, why am I probably going to get one in each of them? We also talked about the coupon collectors problem, right? This is the problem where you had k different coupons you're trying to choose, and every time you got a random coupon, right? So, and you need an extra log k to kind of make sure you got all the coupons. So if you do an extra log k samples, each of these clusters is like a type of coupon. And every time you choose, you're going to get a new one. So you need an extra log k to get 1 point in each of the centers, in each of the clusters. So often, kind of starting with an extra log k factor and then kind of combining together close points will do a good job, a fairly good job of this. Okay, but there's still some adversarial examples, and combining this one, this is not quite the perfect thing either. There's some kind of nuances of how do you combine together close things. Do you have a comment?
I was thinking if k was wrong, even k log k will not help, right?
Yeah, if you have the wrong k,
Yeah.
you may be in trouble. Yeah. So you have to.
I was thinking something based on n instead of k.
Yeah. So so you may run this with a few different values of k and see what you tend to get. You may also choose random centers, and then if you don't like the answer, run it again with a different set of random centers. And do this maybe 5 times and take the answer that gets the smallest cost. That's also another way of doing it. Yeah, so that's a fairly common thing. You randomly select your centers, and do this a few times, and one of them is probably not going to get stuck, right? So if I had picked 2 centers or maybe even 3 centers up here, I probably would have been able to move one down to this point. If I had started with all 3 of them up here. This is kind of a fairly adversarial case here that I've drawn. So if you randomly reselected the centers 5 times, probably one of them would not get stuck in the wrong configuration. Okay, but there's actually a fairly recent new technique, which is kind of a cute combination of this randomly picking points and running this on this Gonzalez algorithm. And it's going to be basically as simple as running Gonzalez, but it's going to be more robust outliers, and it's going to, you can actually, there's some theoretical guarantees to say that it's will be a randomized algorithm, but with high probability you will actually get very close to the right answer for k-means and need a small number of iterations afterwards. So it's kind of the right way to seed k-means. Okay, so this is called k-means plus plus. Okay, so this was a paper by Arthur and Vasilevsky in like 2007. So don't make me try and spell Sergey's name. I think I can do it, but there's a lot of letters in there. Okay, so it's going to be a fairly simple algorithm. So we're going to it's going to look a lot like the Gonzalez algorithm. So we're going to again define this notion as Ci, or Cj is going to be C1, C2 up to Cj. So these are the centers that we've defined so far. So this is our notation again. And so we're going to choose C1 out of the set is going to be equal to some x in set. And this is generally at random. So we're going to pick the first center at random, okay? And so then we're going to again have this for loop for j equals 2 through k. And then we're going to do something a little bit different. Instead of picking the furthest point, we're going to pick choose Cj from x with probability proportional to the distance from x to phi of Cj minus 1 s squared. Okay, so you're going to choose Cj at random from the set. You're going to do it based on this this assignment distance, the squared assignment distance. So the higher the distance, the more likely you are to choose it. Okay, and so this is the whole algorithm. So you can still run it in basically as fast before. You can update these assignment distances very quickly in linear time, and you need to choose this very quickly. Right? So what's going to happen is, if there is an outlier point, it's going to be a very far distance away from my existing center. So I'm more likely to pick it. But if there are a lot more points here, each of these, I have 100 chances to pick each of these points, even though they're half as far as this one. Right? So maybe the distance I'm squaring it, so it's, the distance here is 10, the distance here is 5, then this is then this is 25, and this is going to be it's going to be 100. So I'm going to choose this one 4 times as likely as any one of these, but there are 100 of these, right? So 100 times 25 is much bigger than 100. So I'm more likely to choose something from here if there are a lot of points. If there aren't a lot of points here, then I'm actually better off to minimize my cost function by choosing this one. It's probably not a very clusterable set if I actually want to choose this as a set. But so I'm going to tend not to choose the outliers because there aren't very many of them. And I'm going to tend to pick the points far away from existing centers. All of these points, it's very unlikely I'm going to pick them because they're very close to this center. So that means this value is going to be small. Okay, so there's something I haven't told you. And for some of you who've done a lot of data structures, this may be kind of obvious, but I find for most people, they don't actually know how to do this operation if I haven't told them already. How do you, so you're given a bunch of these weights. So you're going to give a set of these points x. So x1, x2, x3, xn. And each of them is going to have some weight. W1, W2, W3, Wn. And if I'm going to write big W as the sum of Wi. And so note that if this point is actually my center 1, then the distance from this point to the center is going to be 0. So then this weight is going to be equal to 0. So I'll never choose this point. I'll never choose the center. So, but in general, I'm going to have the sum of these weights, and then I want to choose, I'm going to want to choose xi with probability wi over big W. I'll choose it with this probability. Okay, so that's what's going on in this step. Okay, so how do I do this? And again, the only operation, so I'm doing some random algorithm, and the only operation I do is I can choose some u that's uniform in 0, 1. Okay, so I can choose a random value between 0 and 1. That's the only randomness I need is to do this. I can do this a few times if I want to, or maybe I only need to do it once. How do I choose one of these values? How do I do this quickly?
You can pick a random number from 0 through big W, and it's just like, you like partition big W into, I don't know, like your weight 1 is 10, and 0 through 9 will
Yeah, so this is good. Good. So let me help you out a little bit, and we'll get partway there. So this is between 0 and 1, but I want it between 0 and w. So I picked this random u, and then I set u prime equals to u times big W. Now this is equal to, now this is uniform in 0 to big W. Okay, that's good. And now these weights are not quite what I want. I'm going to have for each of these values this Ri, R1, R2. In general, for xi, wi, I'm going to have Ri. This is going to be equal to the sum from j equals 1 to I of wi. Okay, so I'm going to sum up all the weights before here. So this is a very actually useful data structure for a lot of things. Very useful way to store a set of values in sorted order. Or it doesn't even matter. In this case, the order doesn't matter. It's arbitrary, but it's fixed. So instead of storing the individual weights, I've stored what's called the subset sum of the weights. So I can calculate this in linear time. I start with R1 is equal to W1. R2 is equal to W1 plus W2, but actually is equal to R1 plus W2. And in general, Ri is equal to Ri minus 1 plus Wi. So if I scan through them, I can calculate these R values I can do these in
Linear.
I can do these in linear time, right? So after I've calculated all of these values, I can calculate these in linear time. And now I need to choose one of these according to this weight. Okay, now I have this u prime, which is between 0 and w. And these Ri values, these are also between 0 and w. It's going to also be the property that Rn is going to be equal to big W. Okay? So I'm almost there. So now how do I choose one of these values? What?
Maybe it's in the range between Ri minus 1 and Ri, so it is the W.
Yeah, that's right. So what I want to do is to choose xi such that so that xi minus 1 is less than u prime is less than or equal to x. Sorry, these are r. So I can scan through here, and I can wait until I find a value Ri larger than u prime, and that's going to give me. And then I'll choose I'll choose that Ri. I'll choose the xi associated. Okay, so why does this work? Well, instead of writing it this way, you can think of x1, x2, x3, and I can think of assigning them a weight as the distance between these points. Right, so this is going to be 0, this is w, or between 0, this is going to be r1, this is r2, and w is equal to r3. So the weight is the distance between these, and if I pick a random number between 0 and 1, I'm going to choose in this interval proportional to the weight. So this is the right way to choose it. So then if ui, or if u prime falls here, then I'm going to choose x2. So it's between R2 and R1.
You can use a binary search.
Yeah, good. So that's the next point. So you don't actually need to scan these. You can do binary search on these as well, right? So you're trying to find the closest value. You can build a binary tree and find this in only one time. So it turns out here you need to rebuild it after every step, so that's asymptotically may not help, but in practice may be better. And sometimes you need to pick many different random points from a distribution from something like this, and then you want to build a binary tree. Then you can actually select the point in logarithmic time. So. Great. So yeah. So I think this is mainly what I wanted to say about sign-based clustering. Oh yeah. Okay. So there's this other. So this k-means, this Lloyd algorithms is kind of the most standard algorithm if you want to do clustering. This is maybe the first thing you want to think about doing. It generally works very well. It's fast. You can maybe seed it with the k-means ++, and you'll kind of very often avoid these bad situations. Still, this is randomized. It may get into trouble, so you may want to repeat this a constant number of times and take the lowest total score out of all the solutions you get. Okay, so there's a couple of disadvantages of this Lloyd's algorithm, though. One of the nice properties about the Gonzalez algorithm is it works for any metric I have. Right? So let's say I wanted to do this with the Jacquard distance. I wanted to minimize the sum of the Jacquard distances to these centers. How would I do that with Lloyd's algorithm or some k-means algorithm? So can I just run this? Let's see, if I have a set of centers, I can check the distance and find whichever one has the smallest distance, right? So I can do this assignment. That's fine. But how do I compute an average? Does an average make sense of a set of sets? And the Jacquard distance measures the distance between sets, right? How do I take an average of sets? Does anyone have an answer? Okay, good. So I don't have an answer either. So there's not a good way of doing this, right? There's not a notion of what is the average that will minimize this. So one thing you can do is instead of doing average, you can just look at this function, and you want to find a center which minimizes this